So the next topic is going to be on periodic trends in the periodic table. And so one is atom size. So when you look at the orbital shapes, the S, P, and D, you know they have their different shapes. But when you look at the size, that is related to that number n. So the 1s orbital is much smaller than the 2s, and the 3s is even larger. So atoms, as you go down the periodic table, get larger. That trend makes a lot of sense as long as you know that the size of the orbitals depends on the number n. All right, so we'll just put a little arrow saying larger as you go down. Now, the trend that's real tricky is as you go across, they actually get smaller. And that's kind of counterintuitive. Okay, so in this row, potassium through krypton, krypton is the smallest of the atom. This is the largest atom. All right, and so what's going on is that when you put electrons into the same shell, there's you add another proton when you go to the next element, and you add another electron. And so if you add another proton, all the attractions of electrons to the extra proton are energetically favorable. The energy goes down. But if you add another electron, it also repels the other electrons, and the energy goes up. And so the question is, which one of these two dominates the trend as you go across? And so it turns out that of those two terms, the attraction of the extra proton you put in is dominating the trend. And so as you go across the periodic table, you have more and more protons drawing the electrons tighter in because there's more positive charge. The electrons come closer, they're more attracted, and the atom size actually gets smaller. So that's the main reason for that. Okay, it's because the increase of the effective nuclear charge, the positive charge that each electron feels, compared to the repulsion of all the other negative charge in the cloud. That's also the reason that the s and the p orbitals are no longer the same energy once you get past one electron, is because the electrons in these clouds repel each other, and the shapes of the clouds determine how much they repel each other. And so it turns out that the repulsion in the p's is greater than in s, and that's why they're higher energy than so the 2p is higher in energy than the 2s, and that's why we fill the 2s first. All right, so now the trend in the ionization energies is also very important. Okay, and so it turns out as you go down, the ionization energy actually decreases. What that means is when we try to remove an electron from an atom, it's currently attracted to the nucleus and repelled by some of the other electrons. But it always takes energy to remove an electron from an atom. And so it's a matter of how much, though. It turns out that as you go down the periodic table, the electron in the outermost shell is further away from the nucleus, and so it's easier to remove. Okay? It'd be like, you know, if we had a rocket ship out on Pluto, it'd be way easier to escape the solar system than it would be if it was on Mercury, because the gravity of the sun attracts it much stronger if it's closer. So as we go down the periodic table, it's much easier to remove that outermost electron. As we go across, remember we said the electrons were drawn into the nucleus by the increased positive charge. And so as we go across, we're not going to a new shell. So remember this trend, we're going from one shell to the next shell. If we're going across, it's all in the same shell, and the electrons are being drawn in. So it's actually harder to remove an electron from neon than it is lithium. It's harder to remove electron from krypton than it is potassium. And it's particularly difficult to remove electrons from the noble gases. That's why they never lose electrons. Okay? Now the other thing to think about is the opposite. Can you add electrons? All right, so we'll talk more about that in Chapter 6. But those are the trends in the ionization energies. as you go across the periodic table. Okay, I believe that's all I have to say. Good enough.